Alright, last section we have to deal with logs and exponents. So I know some of you guys are giving a big cheer at this point, and some of you guys are like, oh, I really enjoyed this chapter. So anyway, we're going to wrap it up showing you some applications of how this is. The video may be a little bit shorter tonight because so much of it we need to plug into the calculator, and I just can't get you to get a good picture of the screen. So what we're going to do is do as much work as we can setting things up, and we'll see how it works with the calculator and go from there. Alrighty? Alright, so first let's get down a couple of things. I want to talk about your basic formula for growth. Okay? So A is equal to A sub 0 e to the kt. Alright, and I want to go ahead and define what each of these variables mean. So A is equal to, let's define all of them here. We know T is time. A sub 0 is your starting amount. A is your ending amount. And K is the rate of growth or decay. So it's the rate at, say, bacteria is growing, or the rate at which radioactivity is decaying, something like that. Alright, so in class today I gave you guys a note sheet so that you could follow along with me tonight. So if you would, go ahead and grab that, and the rest of our notes will be done there. And also keep your calculator around so that, hopefully we can jump back and forth between the calculator and the worksheet. Alright, so it says in 1990 the population of Africa was 643 million, and by 2000 it had grown to 813 million. A wants us to use the exponential growth model, in which T is the number of years after 1990, to model the data. Alright, so a lot of fancy words there. I want to start with this formula. Now, what does the A stand for? A stands for the ending amount. So in the year 2000, what was the population? 813. So 813 is my A. My A sub 0 is what did I start with? So what was the population in 1990 when I started? So A sub 0 is 643. E remembers your natural base. Now, K is what you're looking for. You don't know the rate of growth, so that's going to stay a K. But we do know the number of years, because what we have data on is from 1990 to 2000. So how many years is that? 10. Okay, now you're going to go back to the idea of solving a exponent, my words out, solving an exponential equation with the natural base. So your job is to isolate K. So first thing, let's divide both sides by 643. Now we're going to go ahead and this time give ourselves some decimals, and we're just all going to agree, since it's real life, we want decimals. Let's round again to the thousandths place. So 1.264 is equal to e to the 10k. Now, you need to get this k out, so you need to get rid of that natural base. So think to yourself, how do you get rid of a natural base? And I hope you said, well, you know what, let's take the natural log of both sides. Because I know that the natural log and the natural base are inverse functions, they will cancel each other out, and I'm left with just 10k is equal to. Now, in your calculators, hit your natural log button, 1.264, and you get 0.234. Now I need k by itself, so I simply divide by 10. And I get 0.023 is equal to k. So that's my constant. Now you're not quite done. What I want you to do now is go back up here to this equation, and let's write our general equation, which is going to allow us to do the rest of our work. Okay, you're not going to know your ending time, but we do know that the population A sub 0 is 643. That won't change. This time we do know K is 0.023. That's our growth constant. And I want it so that I can plug in any value of time and find out. Okay, so this is your general function to represent this growth. Now that's going to help us answer B, because it says, by which year would Africa's population reach 2,000 million? Okay? It's weird, I copied that right from your textbook, but that's an odd number. Okay? So, what would this represent? Would it be the T for time, or would it be the end population? It would be the end population. So I have 2,000 is equal to 643 e to the 0.023, and I want to know how many years that will take. So now you're solving this exponential equation, trying to get t, time t. Alright, so grab your calculators. I'll go ahead and put mine up here. I'm not so sure that you'll be able to see all my work. For some reason, when it backlights, sometimes it gets a little crazy. Alright, so 2,000. The first thing I'm going to do is divide by 643. So I'm going to divide each side by 643. And that gives me 3.110 is equal to e to the 0.023t. Again, your job is to get t by itself. So what do you do at this point to get rid of that natural base? You take a natural log. So I have the natural log of 3.110. So I get 1.135 is equal to the natural log of the natural base. Inverse functions cancel each other out, and I have 0.023t. Now to get t by itself, I just divide. So 1.135 divided by 0.023, and I get 49. Now that's odd, I got something different this time. Oh, I see what I did. Okay, never mind. Sorry, I was looking at the notes that I did before I started the video. I had written down the wrong number. So we're good. You get 49.348 years. So it wants to know by which year will it reach it. Well, the year is either going to be 49 years or 50 years. Do you see that it's going to take it to 50 years to reach this? So take 1990 and add 50 to it, and it'll be in the year 2040 that the population reaches that. Okay? So far, so good. Okay? Let's talk about the next one. The function f of t is given here, and it describes the proportion of correct responses after T learning trials. So T represents the number of learning trials. So the first question wants to know what happens before the trial even takes place. I just throw a bunch of people in a room and I'm like, hey, take this test, see how you do. So if the trial has not yet begun, what is T? So when it hasn't even started, t is at 0. We're at time 0. So I want you to do f of 0, which means you're simply going to go in here, and anywhere you see a t, you're going to put in a 0. Now, when you type this into a calculator, I want to make sure that you remember that this has to go into parentheses. Okay, you also need to put that in parentheses, although I'm hoping you guys just know it's 0. Alright, so let's see if you can see my calculator again. Alright, so 0.8 divided by parentheses. 1 plus e, remember, second natural log, and we said 0. For those of you who had the 84, you had to hit the big arrow to get yourself down to close your parenthesis, and I get 0.4, which means 0.4 people get it correct even before I've given them any of the learning tasks. Okay? Alright, the next one says, what happens after 10 learning trials? So you've put them in and they've done the same thing 10 times. So this time my t is 10. So I'm going to do f of 10. So anywhere again I have a t, this time I'm going to put in 10. Now, a couple of things to note before you grab your calculators. This needs to be in parentheses in the exponent, and the denominator needs to be in parentheses. Alright, so 0.8 divided by parentheses. 1 plus natural base, put your parenthesis in the exponent, negative 0.2 times 10, close your parenthesis in the exponent, get yourself back down, close that parenthesis, press enter. So after 10 trials, 0.705 people are now getting it right. And the last thing I want to know is, what is the maximum? Like, no matter what is the limiting size? So the interesting thing is the limiting size is whatever your numerator is. So in this case, the best I'm ever going to do is 0.8. No matter how many learning trials I give you, that's the best I can hope for. Alright? Oops, excuse me. I just created like an avalanche here. Okay, a couple more to do. Let's flip to the back. Now, I've made a couple of typos here that I need you to fix right off the bat. I apologize that I didn't catch this prior to running them off, but I don't want to waste the paper to go back and do it. First thing, can you cross out 300 and put 30 degrees? If the room temperature was 300, we would be dead. Alright, second thing I need you to do is I actually wrote Newton's law of cooling incorrectly. Please scribble out that first 70 and change it to C. Alright, quick thing about Newton's law of cooling. Again, T is the temperature after. That's the ending temperature. T sub 0 is your starting temperature. And C is the room temperature or the atmosphere temperature. Okay? Alright, so let's get ready to roll. If you want, if we have time, we can go back. Here, we can go back and do it right now. Find your note sheet, and we can go ahead and talk about Newton's law. Okay? So, Newton's law T is equal to C plus T sub 0 minus C e to the kt. Alright, again, we have T, C, T sub 0, K, and T. We know T, again, is time. T sub 0 is your starting temperature. T is your ending temperature. C is your constant temperature, which is typically the air temperature. I'm going to put constant temp. Like if you were baking a cake, it would be 350 degrees. Okay? And then finally, K is the constant. That's what your, that's your rate. So the rate of the temperature change. Alright, you ready to do this one? Alright, so now that we made all the changes for Ms. Hoffman's typos, let's go ahead and read the question. An object is heated to 100 degrees Celsius. It is left to cool at a room that has a temperature of 30 degrees Celsius. After 5 minutes, the temperature of the object is 80 degrees. Use Newton's law of cooling to find the model of the temperature of the object after T minutes. So I want to, again, plug in. So my question is, what is the final temperature of my object? 80 degrees. What is the constant temperature? So what is the room temperature, the atmospheric temperature? 30 degrees. Plus, what was my starting temperature of my object? 100 degrees. Minus the constant again, 30. E, the K is what I don't know, but this time I do have data for a time. How much time transpired? 5 minutes. Okay, let's clean this critter up a little bit. So I have 80 equals 30 plus 70 e to the 5k. Your job is find k. So the first thing you need to do is you need to work to get k by itself. I believe this 30 needs to go. So let's subtract him. And I have 50 is equal to 70 e to the 5k. Alright, again, you're isolating k, so let's go ahead and divide both sides by 70. So on your calculators, 50 divided by 70 gives me 0.714 equals e to the 5k. How do I get rid of that natural base? I'm going to take a natural log of both sides. Alright, so type in the natural log of 0.714. And I get negative 0.337 equals 5k. Now divide by 5. So negative 0.337 divided by 5 gives me k is equal to negative 0.067. Alrighty. Okay, so now go and write your general formula. So I know that this was my general formula for any temperature. My constant temperature of the atmosphere is 30, plus my original temperature was 100, minus 30, E, and I'm running out of room, negative 0.67 T. So let me clean that up for you, because that's pitiful. Can we go ahead and write this as 70 e to the negative 0.067 t? And I apologize, I thought this was going to be a short video, but there was really no way to do it without typing in the numbers. So I'm going to try to finish up this example, and then we'll save number 4 for class. Alright, so B says, what would the object's temperature be after 20 minutes? You now have your general formula. T equals 30 plus 70 e to the negative 0.067 t. And this time, what do you know? You know that your little t is 20. So take out your little t and put in 20. Okay, so let's see if you guys can possibly see this little critter. Alright, 30 plus 70, second natural base, parenthesis, negative 0.067 times 20, close my parentheses, enter. So after 20 minutes, my temperature will be 48.329 degrees. Alright, and the last one says, at what time will the temperature reach 35 degrees? So again, I have my general equation. This time, I want to get an ending time, or ending temperature of 35. So this time I'm going to plug in 35 here and solve for T. Okay, and I think what I'm going to do is go ahead and end the video there and let you guys try to do C and 4 on this page for the rest of your homework. Alright, and we'll go over it tomorrow. You guys have a great night, and I'll talk to you soon. Bye.